Hello friends, let's do our continuation with allylic bromination. Because radical bromination are so selective, they can be used successfully in the library to make alkyl bromides. There are relatively few ways of functionizing an unfunctionalized center, and radical allylic bromination is one of the most effective. We introduced this reaction in chapter 24 where we contrasted the radical reactivity of bromine towards alkene leading to an allyl bromide by hydrogen abstraction. With its ionic reactivity to addition of bromine crosses the alkene, we can now look at a little more detail at the selectivities involved. Here is a typical allylic bromination. NBS N-bromosuccinamide is used to form a small amount of bromine and to keep the bromine concentration low. So NBS is used here. NBS is N-bromosuccinamide. Photolysis of bromine initiate the reaction which then propagate as shown below. The mechanism also illustrates the first aspect of selectivity. Only a green allylic hydrogen is abstracted because the allylic CH bond is considerably weak than the secondary CH bond. There is a problem with this reaction if bromine itself is used because an alternative radical addition reaction can compete with radical abstraction. Competing addition reaction. So, the first step of this competing addition reaction is reversible. The reaction is driven forward by the participation of a second molecule of bromine that trap the product alkyl radical. This side reaction can be prevented if the concentration of bromine in the reaction is kept very low, which is the role of NBS. The alternative competing polar addition of bromine to the alkene is likewise prevented with the low bromine concentration provided by NBS. Although the non-polar solvent CCl4 also disfavor the formation of cationic bromonium ion immediately, while radical halogenation of alkane is used only rarely in the laboratory. Radical allylic bromination of alkene is a versatile and commonly used way of making allylic bromide. Nucleophilic substitution reaction can then be used to convert the bromide to other functional groups. For example, some chemists in Manchester needed to make the two diastereoisomers of 5 tertiary butyl cyclohexane 2 in 1 ol to study their reactions with osmium tetroxide. Tertiary butyl cyclohexane is readily available, so they used a radical allylic bromination to introduce the functional group in the allylic positions, which they convert to the hydroxyl group using aqueous base. Steric effects also play an important role here in the regioselectivity of the reaction. Only the less hinder allylic hydrogen atom further from the tertiary butyl group are removed. Reversing the selectivity, radical substitution of bromine by hydrogen. Radical substitution reaction can also be used to remove functional group from the molecule. A useful reagent for this, and as you will see for other radical reactions too, is tributyl tin hydride Bu3SNH. The SNH is weak and Bu3SNH will react with alkyl halide to replace the hydrogen atom with halogen atom with hydrogen, producing Bu3SNHAl as a byproduct. We discussed the removal of functional group and why you might want to do it in chapter 23. Clearly, for this reaction to be energetically favored, a new bond formed, SNBr and CH, must be stronger than the older bond broken SNH and C halogen. Look at this table of average bond energy and you will see that this is indeed so. The use of tin hydride is crucial to this reaction. SNH bonds are weaker than SNBr bonds while for carbon CH bonds are stronger. Bu3SNH is therefore an effective source of Bu3SN radical and the Bu3SN radical will abstract halogen, particularly iodine or bromine, but also chlorine from organic halides. Breaking a weak C halogen bond are formed a strong SNHAl bond. The complete mechanism of the reaction reveal a chain reaction. Bond representative bond energy kilojoule per mole CBr 280, SNH 303, 308, CH 418, SNBr 552. Initiation propagation homolysis of Bu3SNH is promoted by the initiator AIBN. As you would imagine, the weakest C halogen bond are the easiest to cleave. So alkyl bromide are reduced more rapidly than allyl chloride and allyl fluoride are unreactive. With alkyl iodide and bromide, daylight can be sufficient to initiate the reaction, but with allyl chloride and often with alkyl bromide as well as, it is generally necessary to produce a higher concentration of Bu3SN radical by adding an initiator to the reaction. The best choice is usually AIBN, which you meet early in the chapter. This compound undergo thermal homolysis above 60 degrees Celsius to give nitrile stabilized radical that abstract hydrogen atom from Bu3SNH. So these are the arrows, please note the arrows. Why use AIBN as an initiator? Why not a peroxide? Since we want to cleave only the weak SNH bond, we can get away with using a relatively unreactive nitrile stabilized radical. Peroxide on the other hand generate RO free radical. These are highly reactive and will abstract hydrogen from almost any organic molecule, not just the weak bonded hydrogen atom of the Bu3SNH, and this would lead to side reactions and lack of selectivity. AIBN is needed only in sufficient quantity to be an initiator of the reaction. It is the Bu3SNH that provide the hydrogen atoms that end up in the reaction. So usually you need not 0.02 to 0.05 equivalent of ALBN and slight excess 1-2 equivalents of Bu3SNH. The bond energy of CH2CN is only 360 kJ per mole. A tertiary CH bond next to the CN group should be ever weaker. Bond energy of OH is 460 kJ per mole. Few CH bonds are stronger than 440 kJ per mole. Carbon-carbon bond formation with radicals. You have now met these examples of radical chain reactions. First, radical addition of halogen to double bond, radical substitution of hydrogen by halogen or of halogen by hydrogen. You have seen how the selectivity of these reactions depend upon the bond strength of the bond being formed or broken. Until about 1975, these reactions, with a few exceptions, were all that were expected of radical. Since that date, however, the use of the radical in synthetic chemistry has increased tremendously to the point where complex ring structures such as those of the natural product hizutine or the steroid can be made from simple acyclic precursors in a single radical promoted step. Why has made this all possible is that chemists have learned how to understand the selectivity of the radical reaction to such a degree that they can design starting material and the reagents to define precisely the bond that will break and form during the reactions. We shall now go on to look at the most important consequences of this ability to control radical reactions. They can be used to make carbon carbon bonds. The radical reaction in the margin forms a new carbon carbon bond. The mechanism is quite similar to that of the very first radical reaction we should you right at the beginning of the chapter. You with all you with your additional appreciation of the role of bond strength in the selectivity of radical reaction, you should be able to understand why each step proceeds in a way that it does. First, the weakest bond, CBr, is broken by the light being shone on to the reaction. The second radical, two radicals forms CCl3 radical and Br radical, and it is the CCl3 radical that adds to the less hindered unsubstituted end of the alkene to produce a more stable secondary benzylic radical. This radical abstracts the bromine atom from the BrCCl3, breaking the weakest CBr bond, forming the product and regenerating CCl3 free radical, which adds to the another molecules of alkene. Notice would require Notice that the carbon center radical abstract bromine free radical, not the CCl3 radical, from BrCCl3. To abstract CCl3 radical would require a radical substitution at carbon. Remember, radical wants the easy picking from the front of the display. They do not go nosing around the back to see if there is anything better to be had. The reaction worked quite well, giving 78% of the product, but it relies on the fact that the starting material BrCCl3 has an unusually weak CBr bond. The CCl3 free radical is highly stabilized by those three chlorine atoms. You cannot use most other alkyl bromides for a number of reasons, not least of them being that the product is also an alkyl bromide, and without the selectivity provided by the CCl3 group, the result would be a mixture of polymers. The problem is that we want the product radical to abstract bromine from the starting alkyl bromide to make a new alkyl bromide and a new starting material. There is no energetic driving force behind this transformation. How to make the reaction go this way? Radical 1, alkyl bromide 1, alkyl bromide 2, radical 2, and note this way. For a way of overcoming this problem, let's go back to the reaction we looked at a few pages ago. The dehalogenation of the alkyl bromide by Bu3SNH. The mechanism involves formation of the alkyl radical by abstraction of the Br by Bu3SN free radical. This alkyl radical then just abstract hydrogen from Bu3SNH. Initiation, then propagation. Is it not possible to use this alkyl radical more constructively and encourage it to react with another molecule? The answer is a qualified yes. Look at this reaction. We have add a carbon center radical to the alkene in the radical chain reaction. Here is a mechanism. Something important has happened here. The product radical no longer has to abstract the halogen from the starting material, but instead has to abstract hydrogen from Bu3SNH. It is the Bu3SN free radical thus formed that then regenerates the starting radical. The driving force is provided by formation of CH at the expense of SNH, then SNBr at the expense of CBr. The use of tin hydride increases the power of radical reaction in the organic synthesis tremendously, and all of the steps in this radical chain processes have been studied in great detail because of the importance of the reaction. We will not dwell excessively on these details, but we need to go back and re-examine some points about this reaction because there are some further subtleties that you need to understand. Bear in mind that we have four radicals all in the reaction mixture at the same time, yet each react with its chosen partner, forsaking all others. Let's take each type of radicals in turn and look at the selectivity. Clearly, bond strength has something to do with this. But how do you explain the opposing selectivities of R and nitrile stabilizing radicals? We shall see that the origin of the selectivities impose some restrictions on the type of starting material that can be used for these CC bond forming reactions. Here, radicals react like this, does not react like this. Please understand this. For the tin radical Bu3SN dot, there is a choice of reaction partner. We need it to abstract the halide from the starting material, but it could alternatively add to the alkene. The SNC bond is relatively weak, so addition to the alkene become a significant reaction only if there is a large excess of alkene present and the starting alkyl halide is relatively unreactive. This means that only alkyl bromide and halide iodide are used effectively to form carbon-carbon bond. Alkyl chlorides are too unreactive. The contrasting reactivity of the alkyl radical and nitrile containing radicals need a little more analysis, and we will look at how both concentrations and electronic affect their selectivities. Concentration effect. You know that our free radical is perfectly capable of abstracting hydrogen from Bu3 SNH because that is what happened in the dehalogenation reaction on page number 991. But here a difference reaction happened. Addition to the alkene. In fact, the rate constant for the reaction of alkyl free radicals with Bu3SNH is about the same as that for reaction with acrylonitrile. So that only way in which good yield can be obtained is to ensure that the concentration of acrylonitrile is always at least 10 times that of the tin hydride. The difference in rate will then be sufficient to give 10 times as well as much addition to the alkene as reduction by the tin hydride. Too much acrylonitrile in the reaction mixture cause problem with side reactions. So a good way of achieving this is to add the tin hydride very slowly during the reaction. Offer a device known as syringe pump is used for this. For of course, for complete reaction, the whole equivalent of hydride is necessary, but this can be added over a period of hours. An elegant alternative is to use a technique conceptually similar to the use of NBS to provide a low concentration of bromine for radical allylic substitution instead of adding one equivalent of Bu3SNH. A catalytic amount Bu3SNCl is added at the beginning of the reaction with one equivalent of NBH4. NBH4 will reduce Bu3SNHAl to Bu3SNH. So about 0.1 equivalent of Bu3SNH is formed immediately. With each cycle of the chain reaction, a molecule of this Bu3SNH is converted to Bu3SNBr, which NaBH4 can reduce back to the Bu3SNH. Only as much Bu3SNH is produced as it needed because the rate of production is limited by the rate of reaction. Here Ri plus C double bond CCN in the presence of Bu3SNH catalyst are CH2CH2CN plus Bu2SNI, again NaBH4 stoichiometric Bu3SNH, and this recycle. This method was used in the following example, in which an enantiomerically pure lactone, a useful synthetic building block, was made from naturally occurring glyceraldehyde, a useful alternative to NaBH4 as a reducing agent, particularly when there are reactive carbonyl groups in the molecule, is NaCnBH3, which still reduces Bu3SNHAl but will not touch aldehyde or ketone. Glyceraldehyde to lactone. Frontier orbital effect. The second way to success in making sure that the alkyl radical behave well is to use a reactive radical trap. In fact, this is a major limitation of intermolecular radical carbon-carbon bond forming reaction. For the trapping of alkyl radical, only electrophilic alkene addition to the electron withdrawing group such as CN, COOMe and COMe will do. This is a limitation, but nonetheless, cyclohexyl iodide adds to all these alkene with the yield shown, and the rate of addition to the most of these alkene is 10 raised to power 3 to 10 raised to power 4 times that of the addition to one hexene. 1 hexene. So these are the alkene percent yield. To explain why, we have to go back to our analysis on page number 978 of the electronic structure of radical and the energy of SOMOS. We said there that while both electron withdrawing group and electron donating group will stabilize radical, electron withdrawing group tend to lower the energy of the SOMO, while electron donating group raise the energy of the SOMO. Electrophilic and nucleophilic radical. Lower energy SOMOs are more willing to accept electrons than to give up one. Radicals adjacent to the electron withdrawing groups are therefore electrophilic. High energy SOMOs are more willing to give up an electron than to accept an electron. Radical adjacent to the carbon donating groups are therefore nucleophilic. Here, the preferred reactivity of these alkyl radicals, they are relatively nucleophilic and therefore prefer to react with the electrophilic alkene. Reaction between the nucleophilic alkyl radical and unfunctionalized and therefore nucleophilic alkene is much slow. Similarly, radical adjacent to the electron withdrawing groups do not react well with electrophilic alkenes. We can represent all this on energy profile diagram. So this is the energy profile diagram. Pi, best interaction is with HOMO of nucleophilic alkene, low energy SOMO of the electrophilic radical, and poor interaction with the electrophilic alkene. Poor interaction with the nucleophilic alkene, high energy SOMO of the nucleophilic radicals, best interaction with the LOMO of the electrophilic alkene, frontier orbital of the electron poor alkene, frontier orbital of the electron rich alkene. So these are the cases. We can now consider the third type of radicals in the reaction mixture, highlighting on page number 993. The nitrile stabilized alkyl radical. The diagram above explains the third aspect of radical chemoselectivity in the reaction. Why both the product radicals and the radical produced by AIBN chosen to react with BaO3SNH and not with acrylonitrile? These radicals are electrophilic. They have an electron withdrawing nitrile group attached to the radical center. So reaction with the electron poor alkene is slow. So radical react with, does not react with. Summary of requirement for the successful use of the tin method. Bu3SNH must be added or generated slowly. RX starting material must contain a weak CX bond, Ci or CBr. Radical trap must be an electrophilic alkene, must be present in concentration at least 10 times that of the Bu3SNH. Electrophilic radicals. Having seen having seen the energy diagram above, you will not be surprised to learn that the malonate radical add readily not to the electrophilic alkene but to the nucleophilic alkene, such as this vinyl ether, which carries an electron donating oxygen substituent. The malonate radical is electron deficient. It has a low energy SOMO which interact best with the relatively high energy HOMO of the electron rich nucleophilic alkene. Notice that the reaction work even though a CCl bond needs to be broken to generate a radical. Usually only Ci and CBr bonds can be used. However, this is a very weak CCl bond because the radical produced is so stable. This electrophilic radical can also be formed by H abstraction and by oxidation. This difference in reactivity applied to non-carbon center radical too. For example, the methyl radical CH3 free radical and the chlorine radical Cl radical will both abstract a hydrogen atom from the propionic acid. As you would expect, wait.